Recording is rolling. It is Tuesday, January 14th. We're going to do this rotational inertia lab today. So the question is going to be, what's the rotational inertia of this pipe system rotating about its central vertical axis, right? Here's the setup, right? So you guys have a lab page that looks like this. You guys got a table, and then, well, if you flip your page over, because you guys have pages, right, you guys got some axes set up for a graph, right? Now, how this is paced out so far today is been able to. I wanted to explain this to you guys, remind you guys how this connects to everything we've been learning out for the last week. Okay, we'll get the data, and then that'll take us about to the end of class, and we're going to put this graph together tomorrow. Okay, so that's the plan. Okay, so here I'm going to switch my screen over. So we're going to toggle back and forth today between the stock cam and this webcam over here. Now I've got this in frame. So you guys see this? Okay. So I'm looking at this system right here. Look at that. You guys see how this can rotate back and forth? Now, I feel some resistance to change in motion. Right? Guys, suppose I pop these arms off right here. Right, took the arms off. Guys, if I rotate this now, is it easier to rotate or harder to rotate? Real easy. Look at that. It's almost no resistance to change in motion at all. Right? Pop these arms back on. Right? And then, now it's back to, it's harder to rotate. That's like more rotational inertia, isn't it? Okay? Even if I was blindfolded, I could know whether or not these arms were popped on or not, right? Eccentric, right? So the setup's going to be, you guys see I got the string wrapped around the central axis. It's hanging over the pulley system, and I got some lab weights here. So these lab weights are going to hang down. They're going to fall down, which is going to cause us to rotate. You guys got some stopwatches on your desk? You got time how much time it takes for those lab weights to reach the floor, right? And then we'll be able to make some calculations based on that. Okay, so flip back over to my doc screen because now we're back to the doc cam. Okay, it says, right, because it's going to take us a while to get to the stopwatches and put this whole thing in motion. Because I want to tackle this from a few different other perspectives too. Okay, one is I want to connect this back to some slides you guys have seen over the past week or so. You guys remember these two rotational inertia sticks passed around? Okay, so last semester, how much inertia was just how much mass? That was it, just in the linear sense. Starting last week and this week is now, well, what's the location of that mass? So it's something to do with mr squared. By the way, those rotational inertia sticks are over there by that fire blanket box. Okay, so if you want to get your hands on those at some point, so something to do with mr squared. Okay, so I remember that. Okay, here's some common rigid objects that could rotate. Okay. Inertia is resistance to change in motion. Yeah, resistance to change in motion. Right. So in a linear sense, it's just how much mass. Okay, guys, what if you had a little okay, what if I roll two balls towards you? What if I roll a baseball at you and I roll a bowling ball at you? Right, and I roll them at the same speed. Right. Now, which one probably took more force to get up to that speed? Definitely the bowling ball because it has so much more mass, so much more inertia. And then if I roll them towards you and you got to stop them, which one's easier to stop? Little tiny baseball because it has so much less inertia, right? Okay. And then in a linear sense, it's just like moving back and forth. But in a rotational sense, well, now we got this rotational aspect to it. Okay. So what I really want you guys to see, what I really want to emphasize with this screen especially is, you guys see how each of these is rotating around a defined axis, right? And that's an important part of this too, because if these were rotating around any different axis, it would be a different setup. Like guys, look at the cylinder here versus this coin spinning on its edge. I mean, at a glance, they're both cylinder shapes. They're both the same type shape, right? But they're rotating around different axes, so they get different rotational inertia values. Is that right? Or take a look at this basketball. You see, now this 2/3 mr squared is only if it's spinning around your finger, right? But see if I flip forward a few slides, right? If the basketball is rolling across the floor, it's actually different. So like if you were blindfolded and you like give the basketball a push, so like how much resistance do you feel trying to get it started as you push? It's not 2/3 mr squared. It's actually 5/3 mr squared because the basketball is not rotating about center. It's rotating about this point down here at the bottom, which is like a different amount. This is parallel axis there. Okay? And then same thing, if the basketball was rolling towards you and you brought it to a stop, how much effective inertia would you feel? It'd be like 5/3 mr squared. Okay, to bring. Okay, so resistance to change in motion. How difficult is it to get it in motion? And once it's in motion, how difficult is it to bring it to a stop? Right. So we're talking about this inertia. Right? It's rotational inertia. Right. You guys good so far? Right. Here's the lab setup I just showed you guys. Right. So we got this PVC pipe system. Now it's low friction. There's a little bit of friction, but that'll come back near the end. Right. And then it's rotating around the central vertical axis right here. Right. So we're gonna hook on some lab weight. This lab weight's gonna fall some distance. It's going to cause this to speed up spinning, and we're going to make some. We're going to get some recording measure values and then do some calculations. Okay, you guys get that? Okay. Right. Now, before we do that method, because we're going to put this whole thing in motion, but before that, I want to approach this from a completely different perspective, and then we'll see how closely these numbers align by the end. Okay. So, do you guys see these down here in the bottom left? Rod about center and rod about the end, right? No, this will take us a few minutes to get this. That's okay. Take a few minutes out of here. I want to try this way first because this looks like really similar to my setup. Right? I know there's a central vertical pipe, but that's probably not adding very much inertia to the system. It's mostly those arms that are swinging out, those horizontal arms. Right? So let's try this. What if I do one arm, so it's 1/3 ml squared, and then I just double it? That's probably maybe a lower bound estimate of what the rotational inertia should be. So I'm going to try that. 1/3 ml squared. I'm going to play off that. So I'm going to close this down. Right. Oh, if only I knew the mass of an arm and the length of an arm, right? So let me switch my screen over. Right. So now I've got the webcam going. Okay, so now we're back recording over here. Right. So, what's the mass and the length of this arm right here? Now the length probably pretty easy to get. I just got to measure the length with the meter stick. Actually, I'm going to pop it back here and measure relative to this central axis right here. It's probably a bit more accurate. Right. So I'm looking at, I'm going to call it 63 centimeters. See where you guys can read the centimeters. Guys, does that look like about 63 centimeters right there? You see it? Okay. Let's call it 63 centimeters long. Okay. And what's the mass of this? Well, I don't have a scale, but you know what I do have? Physics knowledge. Do you guys remember back last Thursday, you guys had a torque lab where you guys were doing a seesaw method? Right? I'm about to set up a type system right here. Oh, I got it. You guys see I put this meter stick right at the 50 centimeter mark. It's balanced precariously on this lab weight right here. Right, here's my pivot point. Okay. And if I take a known mass of, let's pop this guy off. I want my 100 grams right here. So I got 100-gram lab mass. I know this one. Okay. And I've got this unknown mass over here. Right? They each have a weight. Okay. All I need to do is park them on the seesaw and slide them around until they balance. See, where's that going to be? Ooh, right about there. Pretty close. That's balanced right there. You guys see that? Really precarious balance right there. Okay. So what's this radial arm and what's this radial arm relative to this pivot point? That's probably the easiest way to solve this. Okay. So I got 10, 25 centimeters. This is 25 centimeters arm this way. This is 10, 20, 30, 37. So I got 25 versus 37 centimeters. You guys see that? Right. All right. Let's put this over here. I'm going to switch my camera back to the dot cam. Okay. I said 25 versus 37. All right. Let's do this calculation. 25, 37. Okay, this one. All right. So what I just showed you guys is I got this seesaw set up. Pivot point at the 50 centimeter mark. Okay. And that was all balanced there. Okay. All right. Then I got my mystery mass on this side. Okay, so put this right here. Try to figure out, hey, I wonder how much mass that is. Well, I know it's causing a weight and therefore a counterclockwise torque. Okay. Oh, and then I have a known lab weight on the other side. Okay. I know this mass is 100 grams. Now, we're usually going to use kilograms today, but every gram, so it's okay. It's got some weight and it's causing a clockwise torque. Calls torque left and torque right. Okay. Is that exactly what you guys did back on Thursday? Right. I think even last semester we used this method briefly to figure out the mass of a pop or something like that. So you guys have seen this a few times before. Okay. So guys, equilibrium, the sum of the torque is equal to what? 0 Newton meters. Okay. So, and I got labeled, whoops, I forgot this. This radial arm here is 25 centimeters, and this radial arm is 37 centimeters. Okay. Okay. So, torque left, I'm just going to throw the negative in there. Minus torque right goes to 0. If I sort of subtract them. Okay. Therefore, if I slide this over, I can say the magnitude of the torque on the left equals the magnitude of the torque on the right. I don't know if that's a little bit overkill, but you guys see this and those have to balance out. That's all. Okay. All right. So I know that torque is R cross F. You guys remember that? Torque is R cross F. Okay. So this radial arm crossed with this force. This radial arm crossed with this force. So I got at 25 centimeters. I have some unknown mass I'm solving for. and then Earth gravity. So mg is the actual force down. Okay? That has to balance out with, on the other side, I got at 37 centimeters away. I've got a known 100 grams and Earth gravity to turn it into a weight. Some mg over here. Okay. Maybe m1g, m2g. Right. Now Earth gravity cancels. So if I took this up to Mars, would it look exactly the same and balance the same, give me the same mass? Yeah. Okay. All right. We're going to solve for this in. All I have to do is divide down 25 centimeters. So what's 37 times 100 over 25? So the mass is, oh yeah, that's exactly what I've been getting in line with earlier. So grams. Okay. And we're going to use base SI units today. So guys, how many kilograms is that? Yeah, 0.148 kilograms. Okay. I tried this before school. I think I got 140 something. The smallest number I got today was 137, and the biggest number I got was 150. Yeah, so this is right in that window. This is what I've been getting all day today. It's the same method. Okay. Plus or minus a few grams. Okay. All right. And oh, I remember the length of this was 63 centimeters, I was using, right? Right. So let's try this out. So I, for a single arm, I say it was 1/3 ml squared, like that. Right. So 1/3, we got 0.148 kilograms. And we got 0.64 meters, and that's being squared. Okay. Okay. Let's see, what is I for an arm? A single arm. So 1/3, 0.148, 0.64 squared, okay, is 0.0202 kilogram meter squared. Okay. I should forewarn you guys, we're going to have a lot of small numbers today because we're putting everything in kilograms and meters. You guys see that? Well, we're not going to use anything that's even a kilogram. And all the lengths are going to be less than a meter. So yeah, we'll have small numbers, right? Now that's for a single arm. Guys, if that's a single arm, remember what this looks like. It's like this T shape, right? Rotating about the central axis, right? Shouldn't I double that to account for the other arm, right? It might be a tiny bit more from the central axis, but hardly anything. So I'm going to say I total. Maybe I'll say minimum, like a minimum boundary value, which is just 2 times this. So times 2, let's call it 0.0404 kilogram meter squared, right? And this is the static method. This is just shopping from that rotational inertia table, popping the M and the L and pop, and it should be out like this, right? Of course, the lab today, which is going to take a bunch of class and go into tomorrow, is we're going to do the version where it's in motion, right? Attach lab weights and watch the thing spin and hold it. Okay, you guys good so far? Okay. Now, just to sort of overkill here, I want you guys to see this trick. This is what we just did. We just did it right about the end, and we said, well, times 2 because there are 2 arms. We just did that. Okay. Guys, could we have done this one instead? The right about the center and sort of treat it like this, 1/12 ml squared? Which, by the way, if you know one of these, you can derive the other if you go through this right here, parallel axis theorem. Just remember that? Okay. So just in principle, you can, but I want to show you guys that in terms of the numbers, it works out. So isn't this full length just twice the length of a single arm? And the mass is twice the mass of a single one? All right. So let's try that version. So let me say I total minimum. I mean, use that other method, 1/12 ml squared, but it's a different m and a different l. So 1/12, in fact, it's twice the mass of what I had before. So 2 times 0.148 kilograms. And it's twice the length of before. So 2 times 0.64 meters. That's again being squared. Okay. I wonder if this is going to give me the same thing as we got before. I mean, it should, right? Physics is all self-consistent. Let's see if it does. 1/12. Right, 2 times the previous mass. And then 2 times the length of a single arm. And that's all being squared. Right? Right. Guys, when I hit enter, let's see if you guys are following. What number better be popping up on my screen? Yeah, 0.0404. Right? Let's see if it is. Aha, it sure is. Look at that. 0.0404. That's kilogram meter squared for rotational inertia. Okay. Okay. All right, you guys good? Okay. So again, we've got small numbers today. That's all right. Okay. I hope by the end of this lab, after we put this whole thing in motion and put that graph together at the end, and blah, 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 right? I hope we're going to get something pretty close to that. Okay? Time will tell. All right. So you guys got this lab table here. Here, I'm going to do my PowerPoint version because it's pretty similar looking lab table and it's easier to read. Right? So you guys see going across? Okay. So we're going to do some measurements and some calculations. Okay, so I tie the string, hook on the lab weight, it follows some distance, x. Okay. So I need to know, or going left to right, measure the radial size of the central axis. Right? That's probably, what, about a centimeter or so? We'll get an exact value for that. Okay. What's the lab weight that I'm going to hang on? Now, this lab weight I'm going to treat as an independent variable. So I'm going to change that out over the course of today. So we'll do that. Okay. What is the distance it falls? That should probably be controlled, right? Whatever distance it falls, we'll just do the same over and over. Okay. Time. Now here's where I'm especially going to need you guys' help. You guys got stopwatches? Okay. So in a few minutes, I'm going to grab 3 volunteers, and we're going to make believe that the 3 different stopwatch values are 3 unique trials, just to save a little bit of time, right? Okay, so we'll get 3 stopwatch times. Okay. That's all the measurements. Guys, those first 4 columns where it says measure, 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 that's all the measurements we need. The rest of these columns are calculations. So there will be enough information where you can calculate what is the linear acceleration of this lab weight falling down, or you can calculate what is the angular acceleration of this rotating, right? What is the tension in the string, which at this radial arm is going to provide a, you guys tell me, guys, what is this R crossed with this tension F? R cross F gives you a what? Huh? A torque. Yeah, torque, which is this Greek letter tau for torque, right? Newtons, meters, Newton meters. Okay, good. Now this last column says I for rotational inertia. I think on your table I did not include that column. There should be no I. Okay. The reason is that I want you guys to get it from a graph. Like if you know torques and you know angular accelerations, you can get it from a graph. Because guys, what formula connects alpha, tau, and I? What's that formula? Here, or give you a hint. Looks like Newton's second law of motion. So let's talk about that a little bit. What is Newton's second law of motion? What does that say? F equals ma, right? No, that was linear. That was last semester. Let's go to this semester. Let's go to this week. Right? It's not F equals ma for rotation. It's what equals what times what. Torque equals I times alpha. Isn't that the rotational equivalent to this? Right? You need a second law. Right? So that force is torque. Instead of mass, that's rotational inertia. Instead of linear acceleration, it's angular acceleration. Right? Okay. Therefore, if you have a bunch of different torque and angular acceleration values, that's what I'm leading up to with this table. Right? Notice I gave you some dark boxes here, so you can take in what's the average angular acceleration, what's the average torque. Right? And if you look at this graph setup, it says torque versus angular acceleration. See, torque versus angular acceleration. Newton meters, radians per second squared. Oh, can you guys look at this formula? The rotational version of Newton's second law. And this set of axes. And make a pretty good prediction. What is this graph going to look like? What shape is that graph going to be? Linear, right? This looks like y equals mx, doesn't it? Y equals mx, right? Right? And if the goal of this lab is to figure out what's the rotational inertia, then what property of this graph is that going to represent? The slope. I bet this is going to be a straight line, and the slope is going to be the answer to the question. You guys think? Right. So I know it's a bunch of setup, but I really want you guys to see forest for the trees, what we're doing before we start plowing through a bunch of numbers. Okay. You guys see that? All right. So let's be getting some numbers here. I need to measure what is the radial size of this. Here, I'll switch my screen. I'm going to do a bunch of toggling back and forth here. Okay. So now I got the webcam going. Oops, let's put this back together. All right. Figure out what's the, maybe I'll measure the diameter and then just divide by 2. So this has a diameter of 2.2 centimeters, right? 2.2 centimeter diameter, which the radius then would be 1.1 centimeters. And we're going to put everything in base SI units. So in this case, meters. Guys, how many meters is that? Yeah, 0.011. There you go. Okay, zoom in there. Is that 0.011 meters is the radius of that central pipe? Right, because the string is wrapped around it, hence this is the radius that's going to apply to the torque. Right? And that will be controlled, guys. That's going to be the same all the way down the lab page. You guys can copy paste that number all the way down. Okay. Now the masses here, I found some good masses to use today. So we're going to start with 150 grams, which is 0.15 kilograms, and then I'll do 0.20, 0.30, 0.40, and 0.50 kilograms. Okay. Okay, guys see those masses? Those are all in kilograms. It's all base SI units. Okay. 0.15, 0.2, 0.3, 0.4, 0.5. Okay. Kilograms. Okay. What's the falling distance in meters? So switch my camera over. Okay, we're back to the webcam. Okay. What is this height change right here? Okay, now the lab weight's going to start a little bit down, so let's just call it an even 70. I think it's pretty close. We'll call it 70. Well, that's centimeters. Okay, so if that's 70 centimeters, how many meters would that be? Yeah, 0.70. Okay, that number will also be the same all the way down, so that'll be controlled. Okay, it's got control, the masses, the independent variable, the falling distance is controlled. Okay, is good. All right, so looks like the measurements are pretty well locked in place, exactly what we're going to do. Except we got to figure out the times. Okay, the falling times is the last measurement, and everything after that's calculations. Okay, see that? The pattern? Okay. All right, so let's see. Okay, get some volunteers. Yes, who wants to volunteer with the stopwatch? How about, all right, let's go. Alexander, let's go. Luciana and Isabel. All right, got Alexander, Luciana, and Isabel volunteering. Yeah, thank you for volunteering. All right, so let's go over here. Okay, so now we're over here. So set up. All right, got this thing ready to rotate. I just need 150 grams because that's the first mass. Gonna hook that right here. All right, boink. Boink. All right. 150 grams. Okay, this is the smallest lab weight we're gonna do, so it's providing just a little bit of tension in the string. It's got some weight, got some tension. All right, you guys ready with the stopwatches? Okay, all right, ready? And go. Ah, look at that. It is moving, isn't it? All right. Almost wasn't sure at first. Okay. Ooh. Hey, is that speeding up? Guys, if it's speeding up, what's that called in physics? Acceleration. Ah, if there's an acceleration, oh, I bet there's a net force and a net torque in this case, right? Yes. All right. All right, halfway down, still going. Pretty close. All right, ready and stop. All right, there it is. Woo. All right, let's go back over to doc cam. Boink. All right, so now we're back up here. All right, see what you guys got. Alexander, what'd you get?
I have 46.5.
46.5 seconds. Luciana. 43 point, I'll call it 43.8. Okay. And then Isabel.
44.09.
44 point, it's called 44.1. There you go. Okay. So you guys got the times. Okay, 46.5, 43.8, 44.1. And again, we're gonna make believe that there's 3 separate trials just to save a little bit of time here. Okay. Okay. All right. That's all the measurements we need. The rest of these are going to be calculations. Now, I'll take you guys through the set of calculations for one of these rows, and then it'll be up to you to fill out the rest of all these tables. Okay. So next column over says acceleration, as in linear acceleration. What's the linear acceleration of a mass falling? Okay. So this is going to be kinematic. And kinematic, do you guys remember this taxi V table I've been doing with you guys? tax EV, just so we can get a checklist and a big picture of what variables we have on the software. So I'm trying to solve what's the acceleration. That's the question. Okay. We got time. I'll write the time here. Pick Alexander's here. You got 46.5 seconds, okay, to go 0.70 meters. And do you know any other kinematic values? What else do you know? Aha! Initial velocity started from rest. Right? That's 3 kinematic values. Which one of these formulas can solve that? First, second, or third? Guys, I'm looking for, guys, what's the only one that has both distance and time and involves acceleration? There's only one of them. The first one. Yeah, first one. Okay. Okay. So let's go. X equals v naught t plus half at squared. Now that's the full version, but I can simplify that. Guys, which term can I just get rid of? V naught t, because it starts from rest. That just zeroes out. Okay. And then I'm solving for this acceleration. So little algebra here. Can I just cross multiply the 2 and divide down t squared? So acceleration is 2x over t squared. Is that true? Right. Which you guys have seen a bunch of times before, right? I also typed it above the column, right? By the way, I typed all the expressions above these columns. See all the calculations? I told you exactly how to calculate it. So a is 2x over t squared, right? But I want to remind you guys where this comes from, where you guys have seen this before. Like I remember, I know during the Atwood lab, this also showed up on the Atwood lab because I'm trying to figure out this so far and so much time with the acceleration. Let's get some numbers in here. So we got 2 times 0.70 meters. This happened all in 46.5 seconds. I got to square that time. Okay. Let's see, what's the acceleration? So 2 times 0.7 over 46.5 squared. Looking at, great. Oh yeah, that's a tiny acceleration. 0.00065 meters per second squared. Yeah, I can believe that. I know Earth gravity is about 10 meters per second squared. I'm actually going to use 9.8 meters per second squared later. Okay. But it was nowhere near free fall. Like it was accelerating so slow. Right. Okay, I can believe that number. Okay. All right, let's pop that in right here. 0.00065 meters per second squared. Okay. Next column, what's the tension in the string? Now, you guys think the tension in the string is pretty dang close to the weight that's falling? Yeah? Okay. Right. In fact, if you just said the tension is equal to the weight, that's probably plenty good enough. Right. I want to get a little more technical with this though. Guys, is the tension of the string a tiny bit more or a tiny bit less than the weight? It's a tiny bit less. And this goes back to elevator physics. You guys remember elevator physics? So I want to go through this with you guys again. Let's set up an elevator. Okay? Because it's like a downward accelerating elevator. That's what it is. Okay? Let's do a free body diagram. So I got mg pulling down, and I got tension pulling up. Now I'll make the tension significantly less than the weight just to really exaggerate, just make it really clear. Okay? And I know net force, so sum of forces equals mass times acceleration. There's Newton's second law of motion. Okay? The net force is, well, I got the weight pulling down minus the tension resisting that results in MA. Okay. And if I solve for that tension, the tension could be mg minus ma. I could factor out the m if I want to. M times g minus a. This looks familiar, right? You guys remember their elevator physics last semester? Right? Like the weight could just be mg, but if it's accelerating down, you have to subtract that off, right? Okay. And that is exactly what I wrote right here. Look at that. M times g minus a. Right? Remind you guys where that comes from. So let's get numerical value. Add 0.15 kilograms lab mass. Okay. And then I'll use 9.8 meters per second squared for pure free fall. So, and then minus, and it was like 0.00065 meters per second squared, right? Which is almost nothing. So this is a real technical step. Right? To my AP students, I mentioned, well, I've even seen AP rubrics where they forget to do the step, although for this one, doesn't really make a difference much anyway. Right? But just to do it, to show you guys. Okay. I'm getting tension is I'll call that 1.47. Or 1.47 what? Guys, what's the unit? Newtons, because it's a tension, is a force, it's going to be in newtons, right? So that goes right here, 1.47 newtons. That's the force that's providing for the torque. Okay. All right. Oh. All right, getting close. Angular acceleration. Ooh, now this is going to connect to turntable physics. You guys remember turntable? I think it's one of my PowerPoint slides I got queued up too, but I'll just draw it out here. So I got a turntable, has some radius, say I have a point that sweeps out some angle, theta. Maybe it goes so far. How far around does it go? X equals theta times r. So here's linear, here's angular, and the connection is just multiplied by r. Okay. A specific version of this, guys, if you go all around the circle, that's called one what around the circle? Starts with the C. Circumference. And what angle is that again in radians? 2 pi. Circumference equals 2 pi r. You guys remember that? Yeah. And then for speed equals omega times r, linear speed v equals omega r. And then a equals alpha times r, right? So alpha is how fast it's speeding up spinning in radians per second squared. A is a tangential acceleration in meters per second squared. So if I want to solve for alpha, I can just do a divided by r, right? Okay, which are numbers that we have. Because here's the linear acceleration of the live weight falling. And here's the radial size of the central pipe the string was wound around. Okay, that's what we need. So I'm going to take 0.00065 meters per second squared, divide by 0.011 meters radial size, and I'm going to get the angular acceleration. All right, and that is 0.059. What's the unit? What's the unit right here? Radians per second squared. Exactly. Yeah. Okay. So that's going to go right here. 0.059. It's radians per second squared. Right? You see that? Okay. And one more cell in this row. What is the torque? Ooh, torque. Guys, torque is what cross what? R cross F. I got the radial size of 0.011 meters. Okay. And then multiply by, and this is the tension force, which is 1.47 newtons. Okay. And if you've forgotten, just threw in the full weight, probably wouldn't make much of a difference anyway. Okay. 0.011 times 1.47. Okay. This is 0.016 Newton meters of torque. Newton meters. Is that true? Okay. It goes right here. 0.016 Newton meters. Okay. And look at there. Now, if I do that for the next two rows and then take an average, right, you guys could punch this in the calculator real fast, right? Then that's going to translate to a point on this graph. Right? Then what we'll do is we're about to swap out the lab weights, right? And so we'll get points, and hopefully they line up in a straight line, like you guys said earlier. Right? Okay, guys, see where this is going? Okay. All right. One point out, I want to make sure I emphasize this. So going back to this PowerPoint, see what is it? This right here. You guys remember the string wrapped around this turntable and you pull it? Zzz, that's kind of a cross section of what we got going on here. Like there could be a cross section of that central pipe. There's a string. What you guys see is, do you guys see that no matter how you pull the string is always going to be perpendicular to this radius. So that's really nice for this cross product because you don't have to multiply by sine of something. Right? It's just always sine of 90 degrees. Right? So R cross F should result in I times alpha. Make sure I hit all my points here. All right. Oh, here's that turntable that I redrew for you guys. You guys remember that? Let's see. Is that all I need? I think I hit all the points I need to hit. Okay. All right. Okay. So you guys ready with the stopwatches? All right, because it's gonna swap out. We're going to make sure my camera switched over. Let's see. Okay, we're back to the webcam. All right, focused on this. I got to rewind this thing. All right, maybe you guys are doing last few calculations while I'm resetting this thing. Got to rewind it. All right, so we had 150 grams to start with. I got to get this up to 200 grams. All right, so here's 200 grams right here. Boink, boink. All right, all set, ready to go. All right, you guys ready to stopwatches? All right, ready and go. Ooh, is that going a little faster than before? Yeah, I think so. It's going a little faster. And stop. Ba-bam. All right, switch back over to dot cam. Back over here. All right, we are back. All right, so Alexander, how much time? 30.09, I'll call it 30.1. Luciana, 30 point, okay, so like 30.3. And then Isabel, 30.0. Oh, look at that. Look at that. Man, you guys are good with those stopwatches. Okay. So, do you guys think you could do the rest of these calculations based on these numbers? Okay, just like I walked you guys through? Just did. All right. You guys go ahead and get some calculations, and I'm going to reset this thing. So, switch my screen back over. Okay, we're back to the webcam. Got to rewind this. You guys are doing some calculations there. All right. And I need to get up to 300 grams. Okay, well, I have 200 on it. So I'll just tag on another 100. That should take care of that. All right. Rewind. Okay. All right. I think we are ready to go. All right. You guys ready with the stopwatches again? All right. Yeah, we'll have a few minutes at the end of class so you guys can do some calculations too. All right. So here we go. Ready and go. Ooh. I think this one's go a little faster, right? It's like subtly faster, but they just tell. Right? Okay, ready and stop. All right, just gonna hold together. All right, so switch back over to webcam, or sorry, dot cam. We're back on the dot cam. Okay. All right, Alexander, what'd you get?
19.9.
19.9. Ooh. Luciana, 20.0. Ooh. Isabel, 19.7. Oh, look at that. They're all like, ooh, within a half second of each other. All right, nice. All right. All right. All right, so back to the webcam. Gonna rewind. All right, reset this. All right, I gotta get 400 grams on here. There's 200 there, 200 here. All right, now I got 400 grams ready to go. 400 grams. All right, guys ready? All right, ready and go. And stop. Wow. Alexander, how much time? 16.7. Luciana, 16.5. Isabel, 16.5 also. Oh, look at that. Oh. All right. So one more set to go. You gotta switch that to half a kilogram coming up. All right, got it on, ready to go. All right, guys ready with the stopwatches? All right, ready and go. Oh, all right, got to stop that. Oh, sorry, did you get that right? Or should I redo that? I'm sorry, got distracted there. We can do redo. Okay, this one's fast anyway, so better mess up this one than the slower ones, right? That's all right. So, my fault. All right, you guys ready again? All right, ready and go. All right, I think that one worked. So, back in. All right, we're back over here. All right, Alexander, how much time? 14.6. Luciana,
14.6.
14.6. And Isabel, 14.1. All right. Yeah, all right in line there. Here you go. All right. We got 10 minutes of class left. That's great. Great. So here's what we do. Here's the rest of class. Go ahead and get these calculations. And for each set, figure out what's the average angular acceleration, what's the average torque. Okay. And that's about where I've been getting my classes up to today. So tomorrow, I'm going to help students put together this graph. So torque versus angular acceleration. I'll make this kind of bit here. So, right, you guys, period 5 right here. Okay, this is torque in Newton meters. And this is angular acceleration in radians per second squared. Right? And we're going to be able to plot 5 points, right? 1, 2, 3, 4, 5 coordinates. Okay? Yeah, then we'll figure out from there. Now, remember, earlier today, here at the beginning of the class, we came up with, well, based on that rotational inertia table, I think the rotational inertia of the system is probably at least 0.04 kilogram meter squared. Okay? So we'll be able to compare and see how this turns out by the end. All right, but for the recording, that's going to be a close on this recording.